Yes, so we will start with angles, and as you know, there are two ways to measure angles. One is the degrees, and the other one is radian. So what is the difference? Well, the degree is probably the one that you have worked with a lot. And in both cases, I would just tell you what is one full revolution. It means that the whole circle, in the case of degree, is 360 degree. And in the case of the radian, it is 2 pi. Well, radian has a nice meaning, which is if you have an angle, you make it central angle in a unit circle, then the length of that piece of circle um, determined by that angle. So what's it called? This length is what the radian is. And something very important is you should keep in mind that in a calculus, when it comes to the calculus, the important thing is radian. So when it comes to integration, differentiation, and when you're doing works related to calculus, you should be able to work with radian. And there's always a way to go between these two. If an angle is d degree, we can turn it to r radian. And the way it works is that, okay, the degree out of 300 degree, the full revolution will be the same thing as r over full revolution in radian. Well, sometimes you see people writing d over 180 equals to r over pi. And that's how we turn these two units, well, we go from one to another one. For example, just go from a angle to radian. So in this case, for example, A, D is 110, and we want to find what is R. Well, you just put it there. And well, I know that D is 110. And right away from there, you see that 110 over 360 times 2 pi. Again, we can simplify and write it 11 over 18 pi. For part B, okay, how about that one? D is a negative 84, and R is then what? So you right away see what's going on, yes. So from there you get, is it 80? 84, yes, okay. So we have minus 84 over 180 pi. You can simplify more, but that's what we need. Is there any specific question over there, Sino? You want? Okay, so we will follow what we had before. So if you have any specific question, please, while I'm doing examples, post it on the chat room. Sino will take care of those ones. And when we stop, he will ask me the question he wanted. And some of them, Sino will help me in answering them. Yes, Sino? Is that
Sure, as long as I can.
Okay, yeah, sure. Thank you. So the other way around, so in this case, R is 3 pi over 7. This is A. Then what is D? So again, a D out of full revolution in degree is 3 pi over 7 over full revolution in radian. Pi's cancel, and then we have D is equal 3 times 360 divided by 7. And so on, yes. So let me just do one more, maybe this one. R is 13 pi over 11, then D over 360 is equal to 13 pi over 11 over 2 pi. You cancel these two, so then the is, why did I put, okay, I forgot that 2 in the above, in that example there. And here now we also have 2 times 11 times nothing else, 13 times 360. That's the degree. And I will leave this one for you as an example. This is just straightforward. Yes, you have to be able to turn the um, degrees to radian and other way. Is there any question, any comments so far?
Nope.
Okay, perfect. So well, when you have the angles, one thing that comes from the classical geometry is that if you have two right triangles, one of such that one of the acute one of the angles other than the right angle, if they have the same thing, so let's say this is another triangle which is right and they have the same angle there, then they are similar, meaning that if you consider the side opposite to that angle, let's say in the small one is opposite O and the big one is O prime, and the hypotenuse here for the small one is H, for the big one is H prime, and the adjacent means that next one, it is one of the sides of that angle actually. In that case, well, we outside A for this, for the big one, A prime. What that classical result says, which is very interesting, it says that the ratio of corresponding uh, the corresponding sides, so for example, O over A prime, or A over A prime, or H over H prime, these are the same thing. So in other words, each one of these quantities is a constant multiple of another one. And well, that's where you see that I can, for example, out of this one, I can put adjacent over H, and it will give me the same number as adjacent prime over H prime. This is the start of trigonometric ratios. It's very important. So each angle fixes a right triangle. And then doesn't matter what kind of right triangle you draw, you may have different things, different right triangles, as you see in this picture, but the ratio of the sides will be the same. And that's where we start to call them trigonometric ratios. These are so important that we fix a name for that. For example, sine of theta is opposite over adjacent. Again, doesn't matter which right triangle you choose, it should have the same theta as one of the angles. And then you can have any sides you like. The important thing is that no matter which one of these triangles you use, that ratio will be the same thing. Cosine of theta is adjacent over hypotenuse, or, well, I'll write just one of these. We already saw that all of them will give you the same thing. And then tan theta will be, well, I can choose opposite over adjacent. And then you can change the order. For example, you can write, how about H over O? Yes, that is 1 over sine, but we have a name for that. And that name is cosecant. So it's the way we write it, CSC of theta, or 1 over cosine theta. It is h over adjacent, which is what we call secant theta, and 1 over tan theta is a over o, which we call it cotan theta. You have three numbers you get from different right triangles with the same theta. Then you choose any two of them, you find the ratio, those are going to be the same thing. So we will have six possible ratios, and those are the angles. Those are called trigonometric ratios for these guys. Okay. Is there any questions so far?
I think very clear.
Okay, thank you. Okay, so let's do, for example, some cases here. If we have a triangle given by the angles and what with the specific angle, and it's enough for us, by the way, to know only two of these sides, then I can find all the trig ratios of those angles. You may say, okay, to define all those all those six ratios, we need three sides. If you have only two of them, how are you going to find the other one? And this is the famous guy, Pythagorean theorem, who has been around long before we could remember, about 2,500 years ago. So it says that if you know two sides of a right triangle, you can find the other one, and it has a good formula. So if this is hypotenuse, you see this is theta, so this is opposite, and this will be adjacent. Then the Pythagorean theorem says that h squared is equal to a squared plus o squared. For example, in this case, we can use that to find a, which is square root of a's length of a side, so it should be positive. So h squared minus o squared, which will give me what? 25 minus 1, and this is root 24. Now that we find this is 24, we can do any of these you like, any of these trig ratios that you want. For example, tan theta, okay, I know it is O over opposite over adjacent. And in this case, it is 1 over, oh, this was root 24. It will be 1 over root 24. And well, you can do a little bit of simplification. Let me do a little bit of simplification, just like this, and this will be 1 over 2 root 6. You can rationalize the denominator, so it will be root 6 over. No, I didn't prepare again anything for this one. But okay, so I will give maybe 1 minute for this one. These are the information given. Find the secant of theta, and post your answer in the chat. Is that okay, Sinan? Can we do that? Yeah. Okay, 1 minute is starting now. This is the right triangle with that theta. Find the secant of that theta for that from that triangle. 1 minute starts now. Okay, I guess it's good. Maybe I solve it and then we check the solutions, how it works. Maybe which one is given more? Can you tell me, Sino, what is the number?
I think all of them are correct,
Okay.
and it's like 8 correct answers so far.
Oh, eight correct answers. So let me then see if I can find another correct answer. Okay, here. Okay, so this is theta. The opposite angle will be, the opposite side will be this. Adjacent is this one. H is this. So from there, we can find A, which is 49 minus 4, and that is 40. Yeah. Well, actually, this is nice number. And 1 over secant theta, what secant theta is 1 over cosine theta. And we know that that is hypotenuse over adjacent. Here we have 7 over 3 over 15. Again, we can rationalize this thing, but you should be able to do these kind of computations. But any of those will be correct answer. Is that the one? Or did I get right answer? Maybe I should ask this way.
Um,
Don't say I got wrong answer.
it is correct.
Thank you. Okay, that's okay. That's good. Well, when you know the ratios and well, for specific, if you have right triangle for a given given triangle, then you can find all the ratios. But some of these angles are important angles, and uh, we have right triangles, at least one of them, that can give us all the numbers we want. So these are the two, I either call them standard triangles or sometimes sample triangles. So standard triangles or special triangles, sorry. Standard or special triangles. So with this thing, we have pi over 3, pi over 6, or pi over 4. You may see me using another version of these triangles. Either you use or will work. So you may see me write 2 there, 1 there, root 3. This is pi over 6, and this is pi over 3. For this other one, you may see me writing 1, 1, root 2. So this is pi over 4, pi over. For those ones, now you have this table. So these are the basic values for these special angles. 0, pi over 6, just to keep in mind that pi over 6 is 30 degree, pi over 4 or 45, pi over 360, and pi over 2 is 90 degrees. So for those ones, we have sine. You have to know this table by heart. So you should remember it. You should use those values whenever it comes for these kind of questions. But and again, you either use this table or memorize this table for this special values, or you just remember these two triangles, special triangles, and those will give you exact same values. And by the way, this last piece here you can get from dividing first row by second row. So every 1 over 2 divided by 3 over root 3 over 2 will give you this, root 2 over 2 divided by root 2 over 2, 1, and so on. Basically, as you saw, it's enough for us to know sine and cosine of an angle. Then everything else, basically, you can make out of those two quantities. Okay. Maybe I stop here and ask if there's any specific question, anything.
Yes, about grading. So they're asking if it's all right to leave the denominator in roots, that I have to rationalize the denominator.
I see. Well, when you write it, I mentioned when I was explaining this thing. Well, for example, like look at this one. Any of these four is correct answer. So if you're replying or you're submitting your assignment, any of these ones you leave at the as a final answer, you're good. But the point is that most of the time you have to be able to see that these guys are equal. Why I'm saying that? Because there are multiple choice questions in this course, yes? So if someone chooses to put this one as one of the option or as the correct option or choice of the multiple choice, you have, and you end up finding this value, you have to be able to transform it to there. If it is writing answer, assignment, any of those forms, those are the same numbers for us, but you have to be able to see how you can change one of these to another one. Yeah, very good.
That was the only question, yeah.
Oh, thank you. Okay, so when you look at these guys, you say, okay, now I know that sine of an angle theta, it acts like a function. You put a theta there, it will give you some number, so that is f theta. That's a function. But so far, since we have defined everything in terms of triangles, remember a right triangle, an angle here, theta, can be only an angle which is less than pi over 2 or bigger than 0. We don't like this. We want something more general. We want to have functions, not just ratios. We want to have function which is defined for all thetas. For this, we need to bring in this convention of unit circle or any circle. So you start there, okay? And then every angle someone gives you, you can place it on this coordinate system that the way I'm going to tell you. First, the vertex of that guy is going to go on the origin. One of the angles, one of the sides of the angle is on the positive x-axis, and the other one, whatever it is, you draw that. And the angles, if you go in the counterclockwise direction, they are going to be counted as a positive. If you go in the negative direction, you're going to count them for negative values. This way, while you have angles of any number, so any theta in R will fix you an angle. It can be positive, it can be negative, it can be bigger than pi over 2, and so on. So this way, we have something that we can bring all thetas in. And then you may ask, what about the trigonometric functions or ratios for thetas defined this way? It is very simple. Every angle you draw, you have exactly one point, which is the intersection of that free side of the triangle, the angle, and the circle. Let's say the circle has ratio r, and then that point has two components, x and y. In that case, sine of theta, we are defining to be y over r. Cosine theta is x over r. Tan theta is y over x. cosecant theta, well, it is r over y. Secant theta, r over x. And cotan theta is x over y. So we define all these things for all thetas, and now we have functions not only defined for these thetas, but also it is defined for all the values of real number, at least for sine and cosine. For tan, well, you have to be a little bit careful. For the other values, you have to be careful because these guys are going to be basically, again, tan theta is sine theta over cosine theta, and cosine theta can be zero at some point. So when you're looking at the domains, you have to be a little bit careful. And right away from here, you see that all trigonometric functions are going to be periodic, meaning that as you go around once and come back, so the angle changes, but the point is the same thing. So if the original angle was theta, now the new angle is 2 pi plus theta, and x and y are the same thing. So that right away tells me that sine 2 pi plus theta is the same thing as sine theta, and for cosine is the same thing. For other trigonometric functions, we have the similar things. Is there any questions so far?
Nope.
Are we good?
Yes.
Okay. So let's do some evaluation of these guys. How do we evaluate the values of these trigonometric functions for general theta? There is one key point that well, you see, we need that x and y and r. Yes, r we can always set it equal to 1. If you set r equal to 1, all these guys are going to be easy to compute. But, well, even if it is general thing, what you need to do is that you use first place the angle on the circle. So for example, in part A, so 8 pi over 3. So what kind of angle is this? So let me see again. This right away, you see that this is 8 of pi over 3. So pi over 3 is, you divide the pi of 180 degrees to 3 equal pieces. Each piece is going to be pi over 3. Now you have 1, 2, 3, and then go here 4, 5, 6, then 7, and then 8. In other words, my angle is starting from here, going around once, and then coming back and hitting this line here. Okay, now let me just erase a little bit of these guys. Okay, nice, nice. Okay, how I can find this funny guy here? Well, place one of these special right triangles, or triangles with special angles, on this um, coordinate, such that one of the sides is on x-axis, either positive or negative. What do I mean here? So you see, there were 3 pieces of pi over 3, pi over 3. So the remaining part here is pi over 3. Let me just get this guy a little bit longer. Now I can place my right triangle with the special angle pi over 3 there. I know what was the length of those guys. This was 2. This was what? This was 1, and this was root. These are just the length, yes? But what I need is point X and Y. So here I want to find the X component. So you look at this guy, I see it's 1 from here. Very nice. And if you go up to there, this is root 3. So root 3 there, X and Y. But you have to be careful. If you write it like that, you have made a big mistake. 1 is the length of that side. Now we are on x-axis and we are going to left, so the coordinate of that guy is going to be negative 1 and root 3. Now we are looking for tan of 8 pi over 3. That is going to be what? Y over x. So it is root 3 over negative 1, which is root.
Negative root 3.
Oh, negative root 3. Yes, thank you. And yeah, so the whole point in this case is that at least the angles that I can relate to my special angles, I can use this trick always. First, place the angle, find the side of the angle which is not on the x-axis, and then try to fit one of these right angles with right triangles with the spatial angle over there such that one of the sides is on the x-axis. Find the coordinates of that point and then use the formulas. Maybe I do one more and I will leave. How about we will do part B. I'll give you 1 minute for the part B and then part C for themselves. So this will be do it yourself at home, but maybe this one, go ahead and try to see if you can give the answer. What is sine of negative 11 pi over 4? And 1 minute is
You are muted.
so okay. So let's see. We have negative 11 pi over 4. Being negative means that we have to go counterclockwise. And 11 over 4 means that we are having 11 of pi over 4. Pi over 4 is half of pi 2. So when I start this way, this will be 1, 2, 3, 4, 5, 6, 7, 8. How many of them we need? 11 of them. 9, 10, and 11. So my angle, I don't need now these guys here. My angle is, we start down here clockwise, go around and come back and go up to that point. Okay. Now, right away, you notice that, okay, I can put pi over 4 here and one of those special triangles with pi over 4 as one of the angles. And you see that this is 1, this is 1, this is root 2. Okay, the coordinate of this guy. Again, remember, 1 is the length of this side, but since we are going down in the y coordinate, that will be -1. This guy is -1 in the left, moving to the left. Okay, so this will be -1. And well, that's it. This is x, this is y, this is r. And we are looking for sine of -11 pi over 4. And that is -1 over root 2, which is the same thing as -√2 over 2. So just bring with yourself the knowledge of knowing trigonometric ratios of special angles, and then this way you can find a little bit more trig values of more angles, but very restricted. They are related to one of those special angles. Sinan, how is there any question, any comments there?
There was a question. I tried to give an example about it, but I didn't receive a response, so let me ask it.
Okay, sure.
Question was tangent pi over 2 plus theta is equal to theta. Is that correct?
And the answer is no. Yeah, yeah. Okay, yeah, the example is like, okay, take, I don't know, easy
Theta equals pi
example
over
would be
4.
what? Okay, yeah, pi over 4 is nice, yes. Tan of pi over 4 is 1. Tan of pi over 2 plus pi over 4 is negative. Something that you get out of this playing with these numbers is, probably you have already watched it in the videos, but I like it to put here as well. So when you have the quadrants, this is the first quadrant, second, third, fourth. What you have to note is that on the quadrants, different ratios will have different sign. And the way it is coded, I like this one, all students take calculus. So all three, by the way, this all here means sine, cosine, and tan. All of them are positive. Only sine is positive. Only tan is positive. Only cosine is positive. So that's how you can keep in mind that, for example, here we were trying to find sine of -11 pi over 4. It was in the third quadrant, and in the third quadrant, only tan is positive. So sine will be negative. So that is, at least sine-wise, we can check it this way sometimes.
Professor, sorry to interrupt. I wonder why can you pull back to the first example, the tan one?
Yeah.
So it goes it goes counterclockwise. Then why is it not the other angle, the bigger angle? Why is it the small angle?
It's not the small angle. Okay, so maybe you could let me see if I understand your question correctly.
My question is, why do you take the triangle from the acute angle, but not the other angle?
But okay, my triangle may look like a little bit strange here, but okay, the point is this. You see, this is pi. Uh, this is pi over 3, yes? Then this is another pi over 3. The remaining part here between these two is pi over 3. So if I want to use one of those triangles, I should put a triangle here which has the pi over 3 angle there, and I will put it like that. You may say, okay, I could have put, because I know that this is, for example, pi over 6. I could have fit the other triangle here. Yeah.
No. What I mean is, why didn't you take the 2 pi over 3?
Oh, I see. Okay, here the question is asking about 8 pi over 3. Okay. But when you go around and come back, it turns out that the result for 2 pi over 3 and 8 pi over 3 will be the same thing, because they will have the same line, they will have the same point, and so on. It's at this stage doesn't matter, you take whichever you want. The point for me was that, okay, first place this angle on the coordinates correctly, and then after that it can be a match with different angles. Okay, in particular it can be matched with 2 pi over 3, or it can be matched with negative 4 pi over 3. All of these guys will give me the same trig function values. Does that answer your question?
Yeah, kind of. Thank you.
Okay. Yeah, so those are just on special values, but then comes, so this is a function. How do we find the graphs of these guys? So the graphs of these guys are something that you should keep in mind for sine, for cosine. Oh, you may say, okay, it's better always when you're trying to graph something, use X and Y. Well, I can do that. For the tan X, I will need a little bit more things there. Okay. So for these ones, this is something that you have. For sine 0 is 0, so it starts from there, goes up, reaches 1, comes back, reaches -1, goes to 0. So where this happens, this is 3 pi over 2, and this is pi over 2. This is pi. This is pi itself, not pi over 2. And then you repeat this. So this is where the periodicity comes in. And you do it like that. You go. For cosine at 0, it is 1. It goes up, down, and then continues this way. For tan, okay, starts like that. At pi over 4, sorry, pi over 2, And negative pi over 2, it has so-called vertical asymptote. We will learn about this thing a little bit more next week, or the videos are already posted. And then you see the same thing is repeating itself. Oh, and so on. So you have from both sides. And so on. So at least these three is the basic ones. You have to be able to draw the other ones, or at least figure out the other ones as well. But main ones are these ones, and make sure that you understand these ones, how this works. Sinan, is there any question there?
There was one, I answered it, but
Okay.
would you like me to read it?
Well, if you feel it would be helpful, just let's go ahead. Yeah, why not?
All right, so the question is, how do we know which quadrant is a certain angle? So for 11 pi over 4, is it like 11 pi over 4 minus 2 pi? Are they equal angles? I think the question.
Okay, yeah, well, anytime you add 2 pi, you're not changing anything in terms of quadrant, in terms of the coordinate. But the way you have to find it is this. So first fix if it is positive or negative. So are you going to go around counterclockwise or clockwise? And then start from there and make sure that you turn it into one of these three special angles, or maybe 4 special angles: pi over 6, pi over 3, pi over 4, and pi over 2. And then count the number of times you pass these guys, and then that at the end you will find what it is there. Okay, is that, are we good there? Yeah, okay. So then let's sketch at least some graphs for trigonometric functions. These are the transformations. So I'll start with the, right away you should see that this guy is some transformation of sine x. So I'll start with the function sine x. And then at the first step, I will multiply x by 3x. I can do a little bit longer so that I can fit the angles also there. So this way I have sine of 3x. Then you see, now I notice that there is this -6. I can generate that -6 not by replacing x by x minus 6. This is not right. The reason is that if I put x minus 6 there, there's a 3 multiplied that, and then that would be 3, 6 minus 18. This is something I don't want. But if instead of that, I do x minus 2, then this will turn to sine of 3x minus 2, but 2 is multiplied by 3, that is negative. So let me just write this as 3x minus 2. And then there is one more step, which is just multiply the whole function by 2. So is it 2 or 3? Yeah, 2. So this will be 2 sine 3x minus 6. And that's the function. Each one of these guys, I know how does that change. So this one, for example, is horizontal shrink by factor 3. This is a horizontal shift 2 units to the left, to the right. And this guy is vertical stretch by factor 2. Okay, So if I start with sine, so I will do that. So I'll try to make sure. And now it's enough to sketch it only for one period. So it will go like this, and then come back, and then go up. Here's pi. Then in the first step, copy, paste. In the first step, we are supposed to do the shrink, vertical shrink by, yes, I should bring it a little bit back. Okay, so the vertical, horizontal shrink by factor 3. So everything will be multiplied by 1/3. So it will go down, down, somewhere there. Basically, the point which before was pi/3, now it will go it will go now to pi/3. The point 2 pi will go to 2 pi/3. Then the next step is, while we are shifting it, copy, paste, we are shifting it a 2 factor to the right. So this one by 2 units to the right. So this one, basically, I pick this, move it 2 units, almost somewhere here, almost. Let me see, pi/3 plus 2. Is that less than pi? Yes, I guess so. Okay, somewhere here. So then this guys now would turn to, this point here is 2 plus pi/3, and this is 2 pi/3 plus 2. And then the last step is, okay, you have this, copy, and then paste. And then what you have is, this is shifting. So sorry, stretch. This is vertical stretch. You do everything by factor 2. Oops. Yeah, something like that. So before it will go from before it will go from -1 to 1. Now it will go from -2. Well, my -2 is now a little bit bigger than what it's supposed to be, from -2 to 2. So that is one period. And then, well, the final answer would be just continue this thing with the same period and same function. Something like that. Okay. Is there any question, any comments there?
There's a question about the precision of the graphs. So wants to know, how do you know how far is 2 units?
Sorry.
How do you know how far is 2 units? Like in tests, is it allowed to just estimate the
Oh, yeah,
graphs?
yeah. Okay, so what I have approximately in mind is pi/3 is approximately 1. Do one make it better? It is 0.4, almost. So it's like, okay, pi was here. Now I want to make it 1/3 of that. And then when you want to shift it up there, you saw that this point, I was trying to compare it by what is the relation between that and pi itself. So pi/3 is 1, almost 1, plus 2. It's almost 3, and it's definitely less than pi. So that's what, that was just an approximation. Is that what the question asks, Sinan? Maybe
I think it's just about drawing the graph, but I think there's a problem with the second graph. So first point of intersection should be just 2, not 2 plus pi over 3.
Oh, this is for this guy.
Yes.
Yeah,
Yes.
okay, so this one, yes, thank you.
Sorry, maybe I misunderstood that. Yeah.
No, 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 no.
No, it's correct.
It could be that I just wrote it there, but you're right. Yes. No, so this is what we shifted from there to there, and this is the 2. Yes, you're right. Thank you. And is that all questions that we have? Like,
Yep.
Okay, so I will leave this one for you to do it yourself. Make sure that you can work with this thing. So the whole point is that you get familiar with these things and you can use them whenever someone wants to do something with these guys. Okay, it seems that we are done with this part. We can actually
Sorry,
sure.
someone just asked, they didn't understand the answer. So,
Oh, the answer of pi over 3, how to compare it with numbers?
I don't think that's the question. The question is how to estimate how far is 2 units.
Oh,
Is 1 unit the value of the translation? So the
oh, I
follow-up
see.
question.
I
So,
see. Okay. So first of all, there is no units here. Yes, you fix it. So meaning what? Meaning that when I sketch this thing, the first graph, I just do it randomly in a nice way. And you know that pi is the point that the graph intercept with the x-axis after 0. Yes? That fixes what is the unit. Pi is about 3.14. So if you fix what is 3.14, you basically have fixed what is 1. 1/3 of that is your unit. Almost, yes. So this is your unit. That's why you see that shifting. I use that pi over 3, and this is 2. So basically, by drawing one of the graphs at the beginning, we fix what is pi. Fixing one of these guys fixes the unit. Does that answer the question?
I think so.
Okay. Should we maybe get a break of like 2-3 minutes? And if they have any specific questions, they can ask at this stage. The second part will be about the identities, inverse, and so on. So if you have a question, you can ask now. Like we will have 3 minutes. This way I can take a little bit break too. Yeah, is there any question? Sinan, if you like
So
to.
far, no.
No? Okay. If there is none, then I would start because I guess we will need these times for this part. Did anything new come up or are we good?
No.
Okay, so when it comes for the trigonometric identities, we have these 3 important package of trigonometric identities. One is the Pythagorean theorem, which is sine squared theta plus cosine squared theta is equal to 1. Then the second one, and this categories are important mathematically, by the way. This is sum and difference formula. And it's enough to know for sine and cosine. So what is sine of theta 1 plus theta 2? This is sine, the first one, cosine, second one, plus sine, second one, cosine, first one. How about cosine of theta 1 plus theta 2? This is cosine of theta 1, cosine of theta 2, minus sine of theta 1, sine of theta 2. And you will see that how we can use these things to evaluate different angles, actually. Well, how about the negative? So the difference. Well, that will work the same way, but you just change the sign of the operation in the middle. So if you start with -1 here, you will change. If you start with -1, you change this one to negative, and you negative here, this will be positive. In the case of cosine, you have to be careful. The sign in between are different. Now, when you put θ1 equal to θ2, then you get what is called double angles. So for those ones, basically you have sine of 2θ. This is equal to, well, θ1 equal to θ2, you will get 2 sine theta cosine theta. For cosine 2 theta, this is important. You will have 3 versions of that. But the first version, which comes up right here, is this will be cosine squared theta minus sine squared theta. Now, you can use this Pythagorean theorem and replace sine squared by 1 minus cosine squared. So that way you will get 2 cosine squared theta minus 1. And then, or you can change cosine squared to 1 minus sine. You will get 1 minus 2 sine squared. And these are all 3 same questions, same formulas, but different forms. In these last two forms, you can solve this thing for cosine squared or sine squared. So cosine squared theta is equal to half of 1 plus cosine 2 theta, and cosine squared theta is 1 minus cosine 2 theta over 2. So this way you will have, but these are the identities. The important thing is that you first know the main formulas, and then you have to be able to get a little bit, not much, but just a little bit, move from here and there, and you will find more useful examples. One of the things, oh, I missed an example here. Did I put it somewhere? Okay, I should need to go grab another. Did I maybe? Let me see. No, okay. So just give me a second. Let me stop sharing, because there are a good example there. I want to bring that example down here. It's very important. Oh, okay. Copy. Back. Okay. Okay, so back. So this is what we have. We can use these formulas to evaluate some of the angles. So, for example, cosine of pi over 8. Why? You say, okay, I have a table. I know how to place it on the, but pi over 8 is not one of the special angles. And if you place it on the coordinate system, you won't be able to find a good relation between those and special angles. But for cosine, so let me just try to cosine pi over 8. The key point is that pi over 8 is half of pi over 2. Sorry, half of pi over 4. How is that going to help me? Well, see the angles here we have? If you have cosine of cosine square of theta is 1 plus cosine of 2 times that theta over 2. Means what? Means that if I set theta to be pi over 8, cosine squared of pi over 8 is 1 plus cosine of 2 times pi over 8 over 2. And this is 1 plus cosine of pi over 4 divided by 2. And well, I know what is cosine of pi over 4. It is root 2 over 2, and there was this 1 over 2 over there. Now, what I found is cosine squared theta is, let me simplify that. This is over 4, 2 plus root 2. And then from there, you see that cosine theta is either plus square root of that, or it is minus. Well, by the way, again, this guy, you can simplify 2 plus root 2 over 2. Yes, it is either plus or minus, but which one is correct? So this is something that you have to see. Pi over 4 is in the first quadrant. Half of that, this is pi over 4, half of that, which is pi over 8, will be in the first quadrant. In the first quadrant, all sine, cosine, and tan, all of them, all students take calculus, all of them are positive. So then we should drop the negative sign here, and it will be just positive. So it will be root cosine of pi over 8 is equal to root 2 plus root 2 over 2. And that's how you find pi of that using that angle. Is there any question, any comments there?
Yes. So the first one is, are these the only identities they need to memorize for this course?
Yes.
Classic.
Yes.
The second one is, could you explain how you got from the double angle cosine formula to all the other ones?
Oh, here. Oh, okay. I can do that one. So here, you see, to go from this to that, what I notice is that sine squared theta is 1 minus cosine squared theta. And plug it in there, there will be, so let me just write here, cosine squared theta minus 1 minus cosine squared theta. And this is cosine squared theta minus 1 plus cosine squared theta. There are 2 of cosine squared thetas minus 1. The reason I'm going fast on these steps is that that's the main idea. To go to this formula, you use sine squared is equal 1 minus cosine squared. To go to the second one is the other form. This time you can write cosine squared as 1 minus sine squared. That's how you go for the third one. And to go to the half angle things, you see these guys, just solve it for cosine squared theta. So take 1 to the other side, so 1 plus cosine 2 theta divided by 2, that's what you'll have. For this one, the same thing. Take 1 to the other side, divided by negative 2, this will be what you get. I hope that answers the question.
I think so. Another question is, for this example, can you also just use the addition identities? which I think would be a bit more difficult.
Yes, okay, so for the addition, you need, how you're going to use addition? Because, yeah, I guess there is something there that you have to be careful. It will be a little bit the other way around. For this one, really, you need the half angle, or you have to go somehow all these steps and prove these things in special case. I would say better, well, the best is use the half angle. Can we do the other one maybe, or do we have more questions,
No more questions.
Okay, let me do part B because this is interesting thing to see. For part B, sine of 7 pi over 12. Okay, so one thing here is that you may say that, okay, this is 7 times pi over 12. Pi over 12 is half of pi over 6. And I can find the formula for 7 times pi over 6. Oh, that's a long story. So you wouldn't go that direction. But instead of that, there is one simple observation. That pi over 3 plus pi over 4 is 7 pi over 12. And then you go from there, use the formula sine of pi over 3 cosine of pi over 4. By the way, why is it important to write it in terms of these guys? Because we have some formula which writes everything in terms of pi over 3 and pi over 4. And pi over 3 and pi over 4 are special angles. And you can use the table to find the values of these guys. And here, sine of pi, this is this is this is that, and this is, oh, this should be cosine. And cosine is 1 over 2. So if I factor out root 2 over 4, this will be root 3 plus 1. And that's what you get. So just write it as sums of two of those special angles, use the sum formula, and you will get the final answer there. Is there any question? Maybe it's a good time to ask again if there's any good question. Okay.
Yeah, I want to ask about the first one. The
Sure,
cosine pi divided by 8.
Yeah.
Yes, can you show me again how to find the value of the given angles?
You mean the quadrant or the whole thing, you mean again?
Oh, the whole thing.
Well, okay, so I won't go over it because I think we had spent enough time here. But what thing was that I used the half angle. So cosine squared theta is 1 plus cosine 2 theta over 2. And then I plugged in pi over 8 for that. Why is this helpful? Because when you multiply pi over 8 by 2, you get pi over 4, and then that is a special angle, and you know what the sine and cosine of that. Then you just do the simplification here, and what we find is that cosine squared of pi over 8 is this. Then you have, we are interested in cosine of pi over 8. Oh, by the way, this theta is pi over 8, really. So this is then you have to find the square root of both sides. But when you find square root, it gives you, it's either plus or minus 1. Which one is that? Well, we know that pi over 8 is in the first quadrant, so that its cosine must be positive. So that's why we get only positive value, and that's how we find this number here. I hope that it was very, I know it was quick, but we already spent enough time on that. Again, if you check that one, if you have more questions, let me know.
I have a question.
Sure.
It's for number B, the sine 7 pi over 12. So I'm not sure if you skipped a step, but shouldn't it supposed to be first as 4 pi over 12 plus 3 pi over 12, and then we would simplify it to pi over 3 plus pi over 4, or did you do something else?
Oh no, so I noticed that maybe I jumped a little bit quick here, but what I noticed is that there is, you see both denominators are 4, and in the numerators we have root 2. So root 2 over 4 is the common factor in both summands. Then if I take that out, basically I'm factoring out root 2 over 4. It will give me root 3 from the first component, or from first summand. And from the second one, there's nothing left. So that's how I got that.
I was actually speaking about like the beginning where it was sine 7 pi over 12, and then it's equal sine pi.
Oh, this is just equality. This is, as I said, so 7 pi over 12 is the same thing as pi over 3 plus pi over 4.
And
The angle itself is equal to that. So it means that their sign will be the same thing.
And you found this out by, because the
This
only
is
way.
sum formula. You see here?
Yeah.
Sine of theta 1 plus theta 2 is sine of first one, cosine of second one, plus sine of second one, cosine of first one.
Yeah, like in my notes, I put 4 pi over 12 plus 3 pi over 12, and then I simplified them to pi over 3 plus pi over 4.
Well, yeah, okay, you can do that one too, but at the end, you're just doing this step, yes? You may take more steps to get there.
Yeah.
But that's good. Okay. Let's do one more example. Okay, so I'm a little bit behind now. Sine 3 squared, let us write it on sine theta. This is just a practice of what we have from the identity. So I will start with sine 3 theta as, I'm writing 3 theta. Well, you may say I can write it theta plus theta plus theta. But I have a formula only for sum of 2 angles. So I will put 1 theta and another 2 theta. And this way we have sine of first one, this is some formula, cosine of 2 theta plus sine of 2 theta cosine of theta. And well, cosine of 2 theta, we have a formula for that. Well, there are 3 formulas. Which one you want me to use? You can use either, but here, let's write this one. Why? Because at the end, we want to write everything in terms of sine theta. So it will be 1 minus 2 sine squared theta plus, and this is 2 sine theta, double angle for sine, cosine theta times cosine theta. This is sine theta. Oh, by the way, so see, there is a factor sine theta, so I can factor that out. And then the remaining is 1 minus 2 sine squared theta plus Well, cosine theta times cosine theta is cosine squared theta. And now, here, cosine theta is 1 minus sine squared theta. Cosine squared theta is 1 minus sine squared. So it will be 1 minus 2 sine squared theta plus 1 minus sine squared theta. And if you put all of them together, you notice that this is 2 minus 3 sine squared theta, and this is 2 sine theta minus 3 sine squared theta. So we wrote sine 3 theta in terms of sine. And again, I'm just using the formulas. Basically, 2 of the formulas, I'm just repeating them. The rest is just algebra. I see. Is there any questions, Sinan, there?
Yeah, I was just answering it. So when working out these problems, how do you know which formula to use in general?
In general, there is no specific thing that will tell you which one is better one. But in this specific case, since we are supposed to write everything in terms of sine, so I went and wrote the formula for double angle in terms of sine. So it will be 1 minus 2 sine squared. Any other?
Yes, could you clarify the steps in this problem once more? There is a problem with the third step. In the line 2, what happened to the 2 in sine 2 theta's expansion?
Oh, I missed it there. Oh,
Yes.
I see. Oh, that was good one. Sorry. Yes, I missed that too. I had the feeling that, okay, so this is what will happen then. Oh, I was happy that, okay, yeah. Oh, okay. Thank you for that.
Let me check because someone's also claiming something else is missing. A sine is still missing.
No, I factored out that sign.
Yes.
You see, there is a bracket here. This and that we factor out. So you see, this is a closed bracket.
And someone says they do not understand the meaning of the question.
The meaning of the question is this: write sine 3 theta in terms of sine theta. That is what really this means. You see, if someone tells me what is sine of 3 times theta, and if I know what is sine of theta, I can just plug it in here, write 3 times that number minus 4 times that number to the power 3. So I was able to find the value of sine 3 theta in terms of sine theta. For example, if someone tells you what is sine theta, if sine theta is, say, some crazy number, say 0.2, 1 over 5, let me write it back. Can you tell me what is sine of 3 theta? Since I have a formula for 3 theta, I don't know what is 3 theta, what is theta itself, but since I have a formula for 3 theta, sine of theta, and I can write sine of 3 theta in terms of sine of theta, I would just go ahead and write 3 times 1 over 5 minus 4 times 1 over 5 to the power 3. So I wrote sine 3 theta, or I found sine of 3 theta just by knowing what is sine of theta. That's what it means. Writing, finding a formula for sine 3 theta in terms of sine theta.
Teacher, I have a question.
Sure.
Yes, teacher. Because in your the line written back. Um, in your second line, you the formula contains the 2 multiplied by sine data, but why this form transformed to the second the third line just lost the 2 times sine data.
So the 2 is still there. That was something that we just fixed. 2 is there, but sine, you see cosine squared times cosine, this is cosine squared. Sine is there because I factor out that sine theta. You see, this term has sine theta, this term has sine theta. I factor it out.
Oh,
so it is there, but I factor out and you don't see it. When...
Okay. And the teacher, I want to tell me one thing is that is it that cosine data plus beta is equal to cosine data cosine beta plus sine
minus.
Huh?
If it is plus cosine of theta, alpha plus beta, if it is plus, then between sign is minus.
Minus. If it is the minus and it is a plus.
Yes, if you're looking for sine of theta 1 minus theta 2, it is cosines minus sines.
Cosine minus sine.
Yes.
I understand.
Okay, you see, this is just the formula written. You have to check the formula first, and everything is clear. Just this is, you can find that in the formula. Plus is plus, minus is plus. Plus is minus, minus is plus. So you have to check that one in the formulas. It's clear. It is not something that I want to spend time.
Teacher, can you return back? I want to take a photo.
You can find those formulas all over this course. There's no need to take this one from here. You can find it on the book. You can find it on some notes that we posted on the web page. They're all there. Don't worry about this part. Okay, so let me go for the inverse function. We are a little bit behind. Maybe before I move there, Sana, is there any?
I think we're clear.
We're clear? Okay, good. So for the inverse, remember that the function takes x and spits out f of x. We are looking for something that takes the other way around. So if you give it a value of the function, it spits back to your x. So if this is y, so you give it y, it will give you back x. Such a thing is called the inverse function. First thing is that inverse function exists if f is 1 to 1. In other words, remember the horizontal line test. So if you draw any horizontal line, it only intersects either once or none with the graph. So such a graph is called, such a function is called one-to-one function. So if your function is one-to-one, then you can find its inverse. And actually, this is if and only if. So whenever you want to talk about the inverse function, you have to make sure that your function is one-to-one. The second thing that I want to mention here, the way it is defined is, well, y is equal to f x if equal to y, then x will be f inverse of y. So that is exactly what I said here. So if you function takes x to y, the inverse function would take y to x. Okay. For example, x cubed is 1 to 1, and its inverse is the third. Its inverse is the third root. In other words, if y is x cubed, then the third root of y is going to be x. That's, as you see, it's the definition. But x squared is not 1 to 1. So the graph you look is like that, and you see that it intersects more than once with that graph. As the definition goes, so this is another fact. Well, it's not fact, it is very close to the definition. F and F inverse satisfy this property that F, if you combine, if you go by F and then come back by F inverse, you will generate the same number. And this will go that way. So here x must be in a domain of f, and here x must be in domain of f inverse. And yes, I had something else to add here, I guess. And okay, so then the question is how we find f inverse. Well, finding f inverse is basically solving an equation. How do you see solving an equation? You see f of x is equal to y. This is an equation. The right hand side has x, left hand side has the number, the variable y. Now you solve it for x, means that separate or isolate x, the right hand side will be everything in terms of y. If you can do that, you have found what is f inverse. So we have done some examples before, but now let me just do one thing here. So again, I want to find the inverse of this guy. So I start with y equals to f of x. Then from there, it means that y is equal to 4x plus 1 over x minus 1. And we want to solve it for x. So we're trying to isolate x, multiply this to the other side, then multiply these guys. And then, while you see, I want to bring all x's one side, all the y's to the other side. So yx minus 4x equals to 1 plus y. And then from there, you factor out x. This is y minus 4. This is 1 plus y. X is 1 plus y over y minus 4. So I have been able to solve this equation for x. When you do that, you basically have found what is f inverse. This is f inverse applied on y. Well, you say always, I like to have functions like applying on f inverse, so replace x and y. From there, you see that y is equal to 1 plus x over x minus 4, and this is f inverse of u. So finding the inverse function is not always easy because solving equations are not easy. And in this case, in these cases, similar cases, you see that how do we proceed? You just try to isolate and solve it for x. Is there any question, any comments that I need to stop for?
I think I answered it, but still, let me
If you
ask
answer,
it. Yoko.
if you
So the
answer,
question is just what does f inverse of f of x equals x represent?
okay, so you answered, then I'm good.
All right.
Okay. Okay, so we have one question for you as do it yourself. Let me just, because there was something that I had to fix here. So these guys are, I forgot this one. So this is 2x minus 1, 2x minus 1, 2x minus 1. Okay, so maybe we give 90, was it 90? Oops. Why do I have this one here? Oh, okay. You know, I forgot to, okay, so I will fix it just right now. Okay, so you have 90 seconds for this, and then the poll will go on right now. So A, this is B, C. So find the inverse of this guy. Mhm. Okay, so you can
I
choose.
think this might be the wrong question, like the options.
Is it? I just put A, B, C, D. Do you,
No, the options, I think, doesn't have the right answer.
isn't this one like just saying A, B, C, D, E for you?
Yes, but in this slide, there is no right answer.
Oh, really? Again, this time?
So,
What is the denominator? There's an issue with the denominator?
I think numerator, not the denominator.
Oh. You see, what is the problem is that in that question, I printed the wrong function here. That's all it says. Oh, okay, I hate this. Okay, and then this is probably x minus 1. No, x minus
3.
3.
Yes.
Okay. Oh, okay. So let me then solve it myself. This is okay. Never didn't work today then. Neither time. Okay. So y equals to x cubed minus 3 over 2x cubed minus 1. We want to solve for x. So this is 2x cubed minus 1 equals to x cubed minus 3. Then from there, this is 2yx cubed minus y equals to x cubed minus 3. From there, I bring this one here and take that one there. And this is 2yx cubed minus x cubed equals to y minus 3. And from here, I factor out x cubed, 2y minus 1 equals to y minus 3. And x cubed is y minus 3, 2y minus 1. Okay. So all these guys are supposed to be minus 3 here, x minus 3, x minus 3 here. Okay, so, but this is, we solved it for x cubed. What is, what we are looking for is x. So to do that, we need to take third root of that guy. Okay, I know what is wrong, where this old mistake came in. So then change x and y, then f inverse of x is basically the third root of x minus 3 over 2x minus 1. Does my screen shows the correct thing now? Okay. Okay, guys, sorry for the, I had a mistake in the choices, but the solution is this one. Basically, we were trying to solve this for this guy, as I showed here. Is there any question that I need to stop and try to solve it?
Not yet.
Okay. So what happens to the graph of function? Well, when you have a function and it is one-to-one, something like this, then the graph of its inverse is basically reflection about the line y equal to x. So you reflect it like this. So every point you reflect, 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 reflect here. And then you see that this will be something like this. So if this guy was the graph of f, now the black one is the graph of f inverse. And that kind of brings in a new transformation, how you can apply this transformation. If you have a graph of function, if it is one-to-one, if you do the reflection about the line y equal to x, you basically going to its inverse. So that's what it means. For example, in this case, if I have a function f and I start, so from f, then I go reflection of x, so reflection of a reflection about y equal to x, then it means that replace f by its inverse. So that will give me f inverse. Then you do another step, which is horizontal shift left by 2. So horizontal shift 2 units left. So that will come by replacing x by x plus 2. So let me just do this. This means that what we are trying to do is the graph, the function, the graph of the function f inverse x plus 2. So that's another operation which only works for the one-to-one function, meaning that replace that guy by the inverse of the function. So that we can put more things in it. I guess we won't have time too much to go into details, but this will be another example which I will give you 1 minute. Yes, 1 minute. Try to see what is the function whose graph can be obtained from the graph of the function f by this kind of transformation. I'm getting right answer. 5 more seconds, maybe. Okay, let's go one by one. So, oops. Okay, so we are looking for a function whose graph is obtained from the graph of a one-to-one function after we apply these 3 steps, these 3 transformations. One is that, okay, y equal to f of x. That's the starting. Then we do apply this operation here. So it says that vertical stretch by factor 2. So it means that we multiply the function by 2f of x. Then the next step is that we want to apply this guy, this transformation. So here you have to be very careful. You're not replacing f by f inverse. You're basically solving this guy for x and then replacing x and y. So means that, okay, if I start from there, so let me do it in blue. So if I start from there, this is f of x equals to y over 2. And then from there, this is x is equal to f inverse of y over 2. Then interchange x and y. Then you have y equals to f inverse of y or x over 2. X over 2. So after this operation, we will get y equals to f inverse of x over 2. And now that you have done that, the third step is easy step. It is just a horizontal shift. It means that we change x to x plus 3, and that will give us y equals to f inverse of x plus 3 over 2. And as you can see, that is C. Okay, good. Again, here the key point was that this is not just replace f by f inverse. The point is that we want to find the inverse of this whole function here, 2fx. It means that solve it for x, replace x and y, and that's how it works. Okay? Okay, so that was another example. Well, at least we can start inverse trig functions. Yes. So one big remark here is that none of trig functions is 1 to 1. Why? It's easy. It is periodic. If you draw a horizontal line in the range, it will intercept with the graph infinitely many times. Look at the sine, the graph of sine function. Yes, any horizontal line between 1 and -1 will intercept with the graph infinitely many times. Well, right away there, you should say, okay, there is no such a thing as inverse trig function. These guys are not one-to-one. And that's a good observation. That's a correct observation. But you should not stop there. The point is that we need to restrict the domain of trig functions such that the function on that domain is one-to-one. So if this is sine function, if I choose my function to be only from pi over 2 to pi over 2, only on this interval here, then that is a one-to-one function. You see, this guy here is a one-to-one function. And well, then I can think of inverse functions. So I restrict the domain of sine to x being between pi over 2 and negative pi over 2. Or for cosine, well, it needs a little bit different domain. So it will go from 0 to pi. Just sketch the graph of cosine. You will notice why this is important. For tan, this will be between negative pi. Okay, so this I have to be a little bit careful. Negative pi over 2 and pi over 2. I cannot plug in pi over 2 or negative pi over 2 in tan, but that's how it works. For cotan x, it will be yes, between 0 and pi. When you have those things, then right away you just say, okay, on these domains, these are one-to-one, and I can define sine inverse, the inverse of sine function. These guys are important, so we have a name for them. That's how we write sine -1. For this guy, we have cosine -1. Actually, we have other names to those ones. It's called arc sine or arc cosine, arc tan. Those are the same things as sine inverse, cosine inverse, tan inverse. And we have those similar things for secant and cosecant. So only on those domains this is true. And when it comes to the functions like this form, what you need to be, well, evaluating sine inverse functions, what you need to do is that, okay, try to find the angle in that interval such that gives you sine of that angle is this guy here. Well, what is the angle theta such that this is √3 over 2, negative √3 over 2. Why you right away said there are infinitely many of them, but there is only one in the interval pi over 2 and negative pi over 2. There's only one there. So that guy is negative pi over 3. So that's why sine inverse of negative √3 over 2 is negative pi over 3. So you go in the backward. Before, we will put in an angle and we find what is the trig ratio. Now we are trying to find what is the angle whose trig ratio is this given value. And here for tan, we know that tan of pi over 6 is 1 over root 3. And we know that pi over 6 is between pi over 2 and negative pi over 2. So we are safe to say that this is pi over 6. For cosine, well, there is only one number, so I'll just go a little bit quicker here. This is pi over 3. And again, pi over 3 is a number between pi and 0. Secant, so what is the angle whose secant is 2? Well, we know that secant is 1 over cosine theta, and that means that cosine theta is 1 over 2, and we already found that that is pi. And time is 9 now. Maybe I have one more example to do. Find the domain of something defined by sine inverse. But maybe, actually I have 2 examples for that. Maybe I should say, let's stop here, see if everyone wants I continue. If not, those who want to stay, you can stay, and I will do these 2 examples before I leave the tutorial. Otherwise, you're welcome to leave, and I guess that will be the end of the tutorial. What do you feel? Do you want me to continue doing these 2 examples?
Maybe we should open a poll for that.
Oh, okay. Okay, it will take a bit time to do that.
So far, people are saying yes, but I cannot count how many. So far, nobody said no. Or we could just say, if you have an objection, please just write that.
So continue, yes or no, yes. Continue, yes. No. Okay. Just give me, if you want to continue now on these 2 examples. Okay.
There is a question about the previous problem.
Sure, yes.
So question is, could you also shift the interval, i.e. Have sine x be restricted to pi over 2 minus 3 pi over 2, which is yes.
Okay, so practically, yes, that's something you can do, but no one does that. So there are conventions in math that you have to fix. This is one of the famous conventions, and you have to use that one. Okay. Okay, it seems that we are good. It seems that 24. Okay, okay, we're good. I can show that. Okay, there are 24. So the key point here is that always. Okay, so this is a fact that you should know, that domain of a function is same thing as one-to-one function, is the same thing as range of the inverse of that, and domain of f inverse is a range of f. And this gives me that a domain of, for example, sine inverse is range of sine. But range of sine, I know that it is -1 and 1. The same goes with domain of cosine inverse. which is again -1 and 1. Domain of tan inverse and domain of cotan inverse. These are the whole real line. Domain of secant inverse and domain of cosecant inverse is, oh, this is a little bit more. So you see the image of secant and cosecant is everything less than -1, including -1, or everything bigger than 1. That's how we have. Now, let's go do this example. If we are looking for the domain of sine inverse, so domain of this function sine inverse of 3x minus 1, this will be all x's such that this guy here that we put inside as input for sine inverse, this guy is between 1 and -1 including. So this guy 3x minus 1 between 1 and -1 means that it is either bigger than -1 or it is, sorry, it should be and here. So it is less than that and bigger than that. Then that means that we can cancel. X is 3x is bigger than 0, so that means x is bigger than 0. And here we have x is less than 2/3. So this is and, so that means that we are looking for all x's such that x is between 0 and 2/3, which will give us 0, 2/3. So that is the domain of that guy there. Okay.
Yeah, can you return back the last page because I want to. Yes, yes,
Is this good?
yes. And the last page,
This one?
maybe last.
Okay, maybe because I will post these ones on the page. So let us just maybe or wait until the end. We will do that there. How about this one? Okay, so domain of secant or the function f. So we are looking for all x's such that x squared minus 1 is in domain of secant inverse of x squared minus 1. But okay, so, oh, sorry, domain of secant squared itself. Domain of secant squared is everything which are less than 1, so x squared minus 1 is less than -1, or x squared minus 1 is bigger than equal to 1. So let's solve this one. This will give me x squared less than equal to 0. Well, x squared is always either positive or 0. It cannot be negative. So this will imply that x squared is 0, so there will be only 1 point here, 0. For this one, we see that x squared can be bigger than equal to 2. And this means that we are trying to solve x squared minus 2 bigger than equal to 2. So find the sign table for x squared minus 2. Over here, this is 0. This will be plus minus plus. So this will give me either x is less than -√2, including that, or it will be √2 up to plus infinity. So we are looking for all x's such that x is either 0 or it's less than equal to -√2 or bigger than equal to positive √2. And that is what we have here as E. Yeah. So basically, this way you have all the domain and all the problems that we had for other trigonometric functions, inverse trigonometric function. Yeah. Okay. Do we have anything, any specific question? No. Okay. So then probably that's maybe a good time. And thank you for everyone waiting for the last thing. We are still trying to get the things done in the right way, especially the timing doesn't make sense still. You know, each week we are covering material for 4 hours in the sessions, but review is only 2 hours. So I'm hoping that as we go on, we will do better and better. And I hope that these sessions are helpful. And well, have a good evening then.
Oh, teacher, I have a question about the last assignment because I have checked my answer. I just made one mistake, but why my final mark is just 51%?
Oh, the assignment one. Okay, P1 is so you have to sign up for office hours and ask those questions in office hours. I cannot answer anything in the class.
Teacher, when is your office hour?
You have to sign up. I have sent out information how to sign up every day from Monday to Thursday, 11 to 12:30. So check the page, check our child page, our tutorial page. You will find the information about how to sign up for office hours.
Okay.
Okay. Is there any question or everyone are partying in the other room? And okay, so we will put all of them in the waiting room.
Thank you.
Oh, thank you. Welcome. Have a great night.
All right.
Okay. Okay. I don't know. Didn't go well. I had two big mistakes, yes. How come this morning I didn't notice that one?
I think the multiple choice question was the same because that's why I just clicked and tried to solve it and verify if it had the same problem.
Yeah, the multiple choice question was the same thing, but the point was, okay, so I solved this once and I did make those answers, choices there. But I guess when I was trying to put what is the function, I put the wrong function there.
Maybe.
That's, I actually have the notes somewhere. I could probably find, yeah, you see, yeah. I start with 2x cubed minus 1 over x cubed minus 3. But what I put here is x cubed minus 3 over 3. That's bad. Okay, I will see what I can do there because this was a good example, I guess. Maybe I should run it once by myself and make a video for that.
Sure.
Okay.
I mean, I think it was clear. Like, I don't think it's a real problem, and I think everybody understood the thing.
I hope so.
But
Sinan, they don't think like we do.
yeah, but I mean, some people asked a few other questions in the chat. I answered them myself and verified that they understood the answer.
Okay.
So
okay.
I didn't want to bother you because, I mean, one of the problems is that when they unmute themselves and interrupt you and ask a question, it takes things way longer, I think, like
Yeah.
5 minutes more.
Yeah,
Because
we should probably, because I guess we can do unmute all and don't allow them to unmute themselves.
that could work.
Yeah, I guess that's something that we should probably do that
I
way.
mean, especially with the first problem, I think we wasted way too much time. Like the when the girl asked the question, because I think there was a miscommunication. She meant something else. You tried to describe something else. I mean, I try to verify what they're asking. I try to understand what they're asking
Yeah,
first, and
that's
then
actually,
give
let's
it to you.
stick to
So
that plan. How about we unmute all at the beginning? Yes, that way probably definitely is better. Yes, unless at the end or at the beginning, like we give them few minutes to do some to ask what, like they ask the question. Otherwise, we go all by chat.
all right, sure. I mean, either way works for me. It's your
Okay.
class.
Okay.
Uh,
Tell me,
also,
Sinan. Okay, yeah, go ahead.
I mean, the same questions come up over and over again in both sections, though we passed the content, so I don't know if it's meaningful, but they've been asking about how to find this, how to apply this horizontal line test, or how to algebraically find if a function is one-to-one.
Yeah, you know, this is always not easy question to answer.
Yeah.
Yes. Yeah, but the reason that some of these things I don't go over in details is that the videos I made have some details for some of these questions.
The reason I brought it up is because if you're gonna shoot a video for that question, the mistaken one, I think that's a good example to show how to find algebraically when it's not one-to-one. For instance, just make it a square root, and then you can say 2x values go to the same y value, so it's not one-to-one.
Okay, okay. That's a good, yeah, sure. Because yeah, if it was root 2x squared instead of that, that would work. Okay, yeah, sure. That's a good thing to keep in mind, actually. I will. Sinan, what do you listen? What kind of sharkils do you listen these days from Turkey?
From Turkey, usually 90s pop songs because they're nostalgic
Like
for me.
what? Like Ibrahim
Do you?
Tatlıses is
No,
here?
no.
No, no. What?
It's an entire different genre.
Okay, tell me a little bit of those.
So do you know a band called Athena?
No.
They're these rock pop band
Oh,
friends from '90s.
okay. So what's the name again?
Athena.
Athena. Turkish pop rock. Oh, so that's
Or
what you like. Athena, okay.
you can look for a band called Duman.
Duman? Okay.
Yeah.
I will try to listen a little bit. I'm more like old style. I
If,
even these days I listen Ibrahim Tatlıses a lot.
if you like that genre, I can also recommend a few things, but I don't usually listen that genre in Turkey. Like
What do you like? So these days, what is new things? Something that it works.
in Arabesk genre, because Ibrahim Tatlıses sings in Arabesk genre almost exclusively. Like
Okay.
in
Okay.
that genre, there is a guy called Müslüm Gürses.
Gil says yes. Okay.
He's very famous, and he's like the OG of that genre. Like everybody worships that guy for some reason.
Okay. Okay.
There is Orhan Gencebay.
Gencebay. Gencebay is alive? Is he still
I'm not
producing?
sure. I think he is alive.
Does he like produce new things?
That I don't know. I mean, I personally. Oh, he's by the way 76 years old. So he's still alive, but very old. I don't think he's producing new things at that age. But I don't like that guy that much for political reasons. So
You don't like him?
Yeah, he's kind of a suck up for government right now, for President Erdogan.
Oh, really?
Yeah, he sucks up a lot. So
Oh, okay.
I don't like guys who just engage in politics in that way in art world. Like either be neutral
Yeah.
or
Well, politician
like,
would be better than those guys, definitely.
yeah,
Because that's their job. I mean, that's their job. Like, no matter.
yeah, they just try to get some side action. Like
So
they
you're
just
not
want
very
to.
fan of this Islamic guys? This
He's not
anti-
Islamic. Like
yeah, I know. Well,
yeah,
you know,
he's
the
more
name.
like a dictator. So
I
wannabe
see.
dictator. So
Yeah, okay.
he's just using Islam as a medium. I mean,
It's
he's
always like that. It's always.
yeah,
Okay.
and don't like is an understatement. So by the way,
Well,
we're still recording.
oh, okay.
So you have some dry